Hi there, it's Mr. O'Reilly here, and this tutorial is going to be on the kinematics of a particle moving in a straight line. Now, kinematics is the branch of mechanics associated with the motion of particles or bodies or even systems of bodies um, without any consideration of the causes of that motion. So you can find me on Twitter at O'Reilly Maths, and you can find my videos on YouTube at O'Reilly Maths also. So the objectives for this tutorial are to understand two of the SUVAT equations and where they come from, and also to use these equations to solve problems involving linear motion of a particle with constant acceleration. So to start off, we're going to get we have to get used to some terms that are going to be used in these problems and the letters that stand for these terms. So the SUVAT equations, as you heard in the objectives, are so called because of the letters SUVAT, which spell out SUVAT. So we have them here on the left. And what they each stand for is S stands for displacement. Now, displacement is the distance in a given direction from a point. Okay, so that's going to be measured if it's a distance in meters. Our U stands for the initial velocity, okay, of a particle. So the initial velocity would be the speed, and against it, velocity is speed in a given direction. So the units for speed are going to be meters per second, or also it can be written as ms to the minus 1. Our third letter then, V, stands for the final velocity. Okay, so that's again speed in a given direction, again measured in meters per second, or ms to the minus 1. And then we have acceleration, which is denoted by the letter A. And acceleration will also have a direction. And acceleration is the rate of change of velocity with respect to time. So that's how your speed is changing as time goes by. So if your speed's measured in meters per second, or your velocity, your acceleration will be how that's changing with respect to time. So that would be meters per second per second. So that can be written as meters per second squared, or also as ms to the minus 2. And then finally we have our time, which is denoted by the letter T, and that's going to be measured in seconds. So we have our SUVAT letters here and what they stand for in the top left. And now we're going to derive two of our SUVAT equations. So as we said already, acceleration is the change in velocity with respect to the change in time. So it's the change in velocity divided by the change in time. So if I just replace acceleration here with our letter A, which we know it stands for, and that's going to be equal to the change in velocity. Well, the change in velocity would be the final velocity, V, minus the initial velocity, U, to represent the change in velocity. And that's going to be divided by the change in time, which will be given the letter T. So we have A is equal to V minus U over T. Now, if we multiply both sides of that equation by T, it gives us AT is equal to V minus U. And then if we add U to both sides, we get AT plus U is equal to V. Finally then we can do a little bit of rearranging and write that with V as the subject, and what we get is V is equal to U plus AT. So of course any of these rearrangements are fine to use, but this is the most common one that you're going to see. So V, our final velocity, is equal to U, our initial velocity, plus our acceleration multiplied by our time. V is equal to U plus AT. That's our first SUVAT equation. Now, as I'm sure you already know, the equation for distance, speed, time is given by the distance is equal to the speed by time. So our distance moved is equal to our average speed multiplied by our time. So distance moved, in our case, we've called that displacement, and we know that's going to be equal to the average speed. Well, the average speed would be the starting speed and the starting velocity and the final velocity divided by 2 to find the average. So we add the two of them, divide by 2 to find the average, and then we multiply that by our time. Okay. So that gives us our second SUVAT equation. S is equal to U plus V all over 2 multiplied by T. So there's our two SUVAT equations. So as you can see on the left here, we have our SUVAT, and we have our two SUVAT equations down here. Now, I did mention earlier that when I was given the definitions, the first four of our SUVAT letters, S, U, V, and A, all these things here have magnitude or size, but they also have direction. Okay, so when we're looking at problems of particles moving in a straight line, we're going to have to decide which direction is positive and which is negative. Okay, so if we have a particle here, P, and it's moving with a velocity 2.5 meters per second from left to right, we have another particle over here moving towards it with a velocity of 6 meters per second in the direction right to left. Okay, now we're going to have to take one direction as positive, so I'm deciding to take the positive direction from left to right. If I do that, well, then there's a few things I could say about particles P and Q. First of all, particle P has a velocity from left to right. Particle P has a velocity of 2.5 meters per second, positive 2.5 meters per second, because it's moving in the positive direction. Particle Q, on the other hand, is moving from right to left against the positive direction, so the velocity for the particle Q would actually be minus 6 meters per second. Now, if we're measuring displacements, okay, we also have to consider the direction, and which is positive and which is negative. So if we decide to measure displacements from this point here, so between the two particles you have this point O, if we decide to measure displacements from here, and left to right is our positive direction, well then our displacements would be as follows. For particle P, the displacement, which is denoted by the letter S, would be minus 4 meters, because it's measured from O, from the point O. It's 4 in the negative direction, that's minus 4 meters. For the particle Q, the displacement will be 3 meters from O, or plus 3, we can just say 3 meters from the point O, so it's from left to right, it's 3 meters in the positive direction. So here's our first problem that we're going to have a look at. A particle is moving in a straight line from A to B with constant acceleration 3 meters per second squared. Its speed at A is 2 meters per second, and it takes 8 seconds to move from A to B. So we're asked to find the speed of the particle at B and the distance from A to B. So the first thing you should always do when you're setting up these questions is to draw a diagram. So if we have a particle starting off here on the left, and we're calling this, starts at A, and it's moving over in a straight line over to B. Well, I'm going to take the positive direction from left to right. And we know that the particle is moving with a constant acceleration, which we are going to measure in the positive direction from left to right again, of 3 meters per second squared. So our acceleration is from left to right. Now the particle A starts off with a velocity of 2 meters per second. So it's moving at point A, the velocity of 2 meters per second. So what I normally denote velocity with a line with one arrowhead, and acceleration as a line with two arrowheads, and then we just have our general positive direction up here. So a good way to approach SUVAT equations is to write out the letters S, U, V, A and T, and to fill in the ones that you are given in the question. So we're given that we're given the acceleration, first of all, is 3 meters per second, so we know that A is 3. We're taking that in the positive direction. We know that speed at A is 2 meters per second, so that's going to be our initial velocity, is 2. And we know it takes 8 seconds to go from A to B, so our time is 8. And what are we asked to find? We're asked to find the speed of the particle at B, so that would be the final velocity, which we need to find out. And we're also asked to find the distance from A to B, that would be the displacement. Well, the best way to approach these questions then is to look at what you have and compare it to our SUVAT equation. So if we have U, A and T, and we're asked to find in the first part, we're asked to find V, well, that's going to be this equation here, because V is equal to U plus AT. So you have 3 of those, and you just need to find V. So we're going to say V is equal to U plus AT. So it's going to be 2 plus A is is equal to 2 plus AT. A is 3 and T is 8. So it's going to be 3 times 8. So it's going to be 2 plus 3 times 8. So that's going to be 2 plus 24, which is 26, and its velocity, so that's going to be meters per second. So that's our V is equal to 26 meters per second, and that's the first part of the question done. So if we're trying the second part of the question here, then we have the distance from A to B. That's what we're looking for now, and we know that the speed from the first part at particle B, the final velocity, is 26 meters per second. So we fill that in over here, and now we're asked to find the distance. Well, if we look at our two SUVAT equations over here on the left, the displacement S is equal to U plus V over 2, all multiplied by T. So that's the equation we're going to use the second one. We know S is equal to U plus V, which is 2 plus 26. That's all over 2. And that's going to be multiplied by our T, which is our time, which is 8. So when we work that out, we get this, let's say, to be 14 times 8. And 14 times 8 is equal to 112. And we know that displacement is measured in meters. So that's the answer to the second part. Our displacement is 112 meters. Okay. If you'd like to have a go at this question now, you can. Just remember to set up the diagram first and then fill in what S, U, V, A and T, which of those that you have from the question, and see if you can decide which equations you need to use to find the distance and the acceleration. Okay, so a cyclist is traveling along a straight road. She accelerates at a constant rate from a speed of 4 meters per second to a speed of 7.5 meters per second. 40 seconds it takes. And we're asked to find the distance traveled over this 40 seconds and also the acceleration over the 40 seconds. So as always, we're going to start off with a diagram. We're traveling in a straight line. We've got our cyclist starts off here, finishes up over there. So the cyclist starts with a speed of 4 meters per second. And it finishes up over here with a speed of 7 meters per second. Okay, now I'm going to take the positive direction again to be from right to left. Okay. So, what can we fill in from our SUVATs? Here we can say that the distance is what we're looking for, s. We know that u is the initial velocity, that's 4. V is the final velocity, which is 7.5. A is what we're asked for in the second part of the question. And our time t, we know, is 40 seconds. So we have u, v, t, and the first thing we need to find is distance or displacement, s. So we're going to be using this equation first of all. S is equal to u plus v over 2 multiplied by t. So S, what we're looking for, is equal to u plus v. So that's going to be 4 plus 7.5. Well, that's all divided by 2. And we're going to multiply all that by t, by our time, which is 40 seconds. So when we work all of that out, put that in the calculator, and we get that is equal to 230 meters, because that is our units for displacement. So that's the answer to the first part. S is equal to 230 meters. So we have 230 meters for the first part, and now we're asked to find the acceleration over the 40 seconds. So now we need to find A. Well, A is in our first SUVAT equation, V is equal to U plus AT. So that's the equation we're going to use. So we're going to say V, which we know is 7.5. We know that's equal to U, which is 4, plus AT. Well, A is what we're looking for, and multiplied by T, well, T is 40, so that's going to be 40 A. So if we subtract 4 from both sides, we get 7.5 minus the 4 is 3.5. And that's equal to our 40A. So then A will be equal to 3.5 divided by 40. And when we put that in the calculator, 3.5 divided by 40, that gives us 0.0875. And that's acceleration. The units for acceleration is meters per second squared. So that's the answer to the second part. The acceleration is 0.0875 meters per second squared. Okay, so moving on to our next problem. This time it says the particle moves in a straight line from a point A to B with constant deceleration of 1.5 meters per second squared. The speed of the particle is at A is 8 meters per second, and the speed of the particle at B is 2 meters per second. Find the time taken for the particle to get from A to B, and secondly, find the distance from A to B. So this time we've got a new term here, which is deceleration. Now obviously deceleration means to get slower, so that's going to be the opposite basically to acceleration. So the first thing we're going to do is we're going to start with the diagram. Okay, so we've got our particle on the left at the point A, and it's moving over here to the point B. Now again, I'm going to take left to right to be positive. Now this time it says we've got a deceleration of 1.5 meters per second squared. Now a deceleration of 1.5 meters per second squared is the same as an acceleration of minus 1.5 meters per second squared. So if we're taking the acceleration in this direction, well then we know that the deceleration in this case is going to be back this way. Minus 1.5 meters per second squared. Now our initial speed, our initial velocity for at the particle A, or at point A rather, is 8 meters per second. At point B, the particle has a velocity of 2 meters per second. So that's what we would expect. If the particle is decelerating, we would expect that it starts off with a higher velocity than when it finishes. So we can fill in what we know over here. Well, we know that S is what we're looking for in the second part, the distance from A to B, so S is what we're looking for. We know our initial velocity is 8 at the point A. We know our final velocity is 2, point B. And we know our acceleration is minus 1.5 in this case, because the deceleration is 1.5, and the acceleration will be minus 1.5. And t is also what we're looking for. So we've got u, v, and a, and we're asked to find s and t. The first bit it asks us to find the time taken, so we're looking for t. So if we have u, v, and a, well, we've got u, v, a, and we're looking for t. That's going to be our first SUVAT equation, v is equal to u plus at. So let's set that up. V, which is 2, is equal to u, which is 8, plus at. Now a is minus 1.5, and that's multiplied by 2. So that becomes 2 is equal to 8 minus 1.5 t. When we rearrange that, we get minus 6 is equal to minus 1.5 t. That was adding or subtracting 8 from both sides rather. And finally that gives us t is equal to minus 6 divided by minus 1.5. And that gives us an answer of 4. So our t is equal to 4 seconds. And that's the answer to the first part. Moving on then to the second part, it asks us for the distance from A to B. So we know now that our time is t, we've put that in down here. We're trying to find our distance s, so we're going to have to use our second SUVAT equation. So let's set that up. S is equal to u plus v over 2, so that's going to be 8 plus 2 all divided by 2. And that's all multiplied by our time, which we worked out in the first part as 4 seconds. So that becomes 8 plus 2 is 10 divided by 2, which is 5 times 4. So our distance S is 20. And again, that's going to be meters. And that's the answer to part 2. The distance from A to B is 20 meters. Okay, finally we're going to have a look at one last problem. And this problem reads as follows. A car moves from traffic lights along a straight road with constant acceleration. The car starts from rest at the traffic lights and 30 seconds later passes a speed trap where it is travelling at 45 kilometers per hour. We're asked to find the acceleration of the car and the distance between the traffic lights and the speed trap. So, the first thing you should notice here is that our speed, the car starts from rest at the traffic lights and 30 seconds later passes a speed trap where it is traveling at 45 kilometers per hour. Okay, so the first thing we're going to have to do is we're going to have to change this final velocity here from kilometers per hour into meters per second, because they're the units that we want to use, meters per second. So that's the first thing we're going to do. Well, 45 kilometers per hour, HR to the minus 1. Well, let's convert that. First of all, let's convert it into meters per hour, first of all. So 45 kilometers per hour would be the same as 45,000 meters per hour, because there's 1,000 meters in a kilometer. So 45 kilometers per hour is equal to 45,000 meters per hour. And then what we want to do is we want to convert those meters per hour into meters per second. Well, if there's we need to know how many seconds there are in an hour. Well, if there's 60 seconds in a minute and 60 minutes in an hour, that means there's 3,600 seconds in an hour. So we need to divide the 45,000 by 3,600. And when we do that, that gives us 12.5 meters per second. So, well, now we can draw our diagram. We've got our car starting here, starting at the lights, and it's moving over here to the trap. And again, we're going to take the positive direction from left to right. It's going to be a positive direction. So let's start to fill in, well, at the lights rather. It's starting at the lights from rest. That means that the car starts with an initial velocity of 0. If it's starting from rest, it's 0 meters per second. When it gets to the traps, it's at what we just worked out, 12.5. Meters per second. And we know that it takes 30 seconds to do that. So we're going to fill in what we know over here. We have our U, which is 0. We have V, which is 12.5. We have our T, our time, which is 30 seconds. And we're asked to find the acceleration A in the first part, and then the distance between the traffic lights and the speed trap, which is the displacement in the second part. So to find the acceleration first, that's going to be our first SUVAT equation. V is equal to U plus AT. So we're just going to set that one up first. So that is V, which is 12.5. And that's equal to U plus AT. Well, U is 0, plus A is what we're looking for, and multiplied by T is 30, so that's 30A. So what we get then is 12.5 is equal to 30A. That means that A is equal to 12.5 divided by 30. And when we work that out, that gives us 5/12. Acceleration is 5/12. If it's as a fraction, you can leave it as a fraction. So 5/12, and that's going to be meters per second squared for acceleration. That's 5/12 meter per second squared. So you can use exact answers like this. Moving on to the second part of the question then, the acceleration of the car, which we just worked out, is 5/12 meters per second squared. And the second part asks us to find the distance between the traffic lights and the speed trap. So that's our distance, which is displacement, S. So we're obviously going to use the second SUVAT equation here. So that's going to give us S is equal to U plus V, which is going to be 0 plus 12.5. That's all divided by 2. And that is all going to be multiplied by our time, which is 30. So when we work that out in the calculator, that then gives us 187.5, and it's displacement measured in meters, so 187.5 meters. And that's the answer to the second part. So that's the end of this tutorial on the kinematics of a particle moving in a straight line.